Welcome to Tech Bytes and News, your daily roundup of articles featured in Hacker News. Today, we're diving into the fascinating world of reinforcement learning, specifically a really well-structured reference guide I found. It's like a problem-solution roadmap for tackling RL challenges. Incredibly useful.
Oh, I'm all ears. Reinforcement learning is a field I've been wanting to explore more deeply. What's the core idea behind this reference guide?
It's structured as a series of problems and solutions, each building upon the previous one. It starts with the fundamental problem of finding optimal policies in a Markov decision process, MDP. Think of it as a step-by-step guide to solving increasingly complex RL problems.
So it begins with the basics, like using linear programming to find the optimal value vector? But then it quickly points out the computational limitations, right?
Exactly. Linear programming is slow, so it introduces value iteration and policy iteration as more efficient alternatives. Value iteration iteratively refines value estimates until convergence, while policy iteration iteratively improves the policy itself. It's a beautiful interplay of computation and strategy.
I see. And then it moves on to situations where you don't have complete knowledge of the MDP, right? Like in real-world robotics, where you can't possibly enumerate every state and action.
Precisely. That's where Monte Carlo methods come in. Instead of relying on complete knowledge, you sample trajectories and estimate values based on observed rewards. It's a more practical approach for complex, real-world scenarios. But it has its own challenges, like high variance and the need for exploring starts.
Right, exploring starts. That's where you randomly initialize episodes to ensure exploration of all state action pairs. But that's not always feasible. So it introduces epsilon-greedy strategies.
Exactly. Epsilon-greedy balances exploration and exploitation. It's a clever way to manage the exploration-exploitation dilemma. And then it tackles off-policy learning, where you evaluate a policy without modifying it for exploration, using important sampling to correct for the differences between the behavior and target policies.
That's a really important point. Off-policy learning is crucial in many real-world applications where you can't directly manipulate the agent's behavior during evaluation. But Monte Carlo methods have high variance and require waiting for episode completion.
That's where temporal difference, TD, learning comes in. TD learning bootstraps, using the reward plus the estimated value of the next state as a target. It's more efficient than Monte Carlo, but it introduces bias. It then discusses SARSA and Q-learning, two popular TD control algorithms.
And the differences between SARSA and Q-learning are subtle but significant, right? SARSA is on policy, while Q-learning is off policy, leading to different convergence properties. And then it tackles the challenges of function approximation, using neural networks to handle large state spaces.
Absolutely. The guide then delves into policy gradient methods, which directly optimize the policy parameters instead of relying on value functions. It covers various policy gradient algorithms, including reinforce, actor-critic methods, TRPO, and PPO. Each algorithm addresses specific challenges, such as high variance in updates or instability during training. It's a comprehensive overview of modern RL techniques.
Wow, this sounds incredibly thorough. It seems to cover almost every major algorithm and its associated challenges. It's like a complete curriculum in itself. The way it presents the problems and solutions is really effective. I'm definitely going to check out this reference guide.
I highly recommend it. It's a fantastic resource for anyone wanting to learn or deepen their understanding of reinforcement learning. It's a clear, concise, and well-structured guide that systematically builds upon fundamental concepts. And that's all the time we have for today's episode of Tech Bytes and News. Thanks for listening, and we'll see you next time. Goodbye.
Bye-bye.